Hello everyone. Today I'm gonna explain an exercise, a dynamics exercise, and it's my first video speaking in English. So I hope you enjoy it and can understand my English. Well, at first we have an infinitive rigid bar, frictionless, that rotates respect this point. Inside the bar we have a mass, okay, that can go outward or inward. But that depends. That's the question. We have to determine the minimum angular velocity, constant angular velocity, that makes the mass go outward. Okay? Why? Because we have the effect of the gravity. And what makes the gravity on the mass is that it will be turned inward, right? Like this. So we have to determine the velocity, that angular velocity. Obviously, before this position, the vertical position, p and a half, it's gonna be downward. Okay, but first we're gonna use Lagrange mechanics. What is the Lagrangian? Is this the kinetical and the potential energy, and we can express this in these coordinates. Theta, the radial and the angular. So we're gonna have those two constraints are in theta. So we can express the kinetic energy like this: half the mass plus the velocity squared. But in this plane it's like the radial velocity plus the angular velocity. And the potential energy is going to be mg r sine of theta. So once we have that, we have to express the Lagrangian. They're going to be 1/2 m r dot squared plus, well, this mg r sine of theta. Okay, with that, the equation of motion from the Lagrange mechanics is the derivative of time. Well, that is like this. So first we're gonna work with this constraint, the radial constraint. For that we have to see that the radial constant appears here and here. So we are going to have 1/2 of the mass plus 0 plus 2 plus r plus theta squared minus mg sine of theta. Okay, that's eliminated from the derivative. Okay, so this is like, let me move this. This is like m r theta squared minus mg sine of theta. Okay, then we take this derivative from respect to velocity and just appears right here. So we're gonna have 1/2 of m 2 plus r dot. So it's m r dot. And from this we take the derivative respect time, and we have m r double dot. And with m r double dot we have the solution, right? That is this minus this expression plus mg sine of theta equals to 0. And we take the mass, and this is a solution. But we want the solution. We want to know the critical velocity, angular velocity. How can I do that? Well, first I want to show you that theta is gonna be omega, the angular velocity respect time, assuming, well, theta dot is omega, right? And using this, we can express also like this expression. And what is this? This is a constant, this is a constant, this is a constant, and we have this derivative. As you can see, it's an differential equation, right? ODE, ordinary differential equation, and that's the solution. So for that, to solve this mathematical equation, I use MATLAB, and we're gonna see the graphs. This is code for you. I write it. It's very easy, right? And I use like initial position r sub 0, and it expresses like an expression, and the radial velocity, initial radial velocity is gonna be 0. So this is a solution, as you can see right here. And I want to express it like in graphs to understand what is happening. And we have the radial position, the angular velocity, and the time. If we look up here, we're gonna see this. And what is this? Well, these are gonna say that is a stabilization points. How? Because if you can see, it starts like in R0, but for this graph, I put like that R0 is equal to 10. So that color is 10 in this part. And we can see that this is a stabilization point. So, as we can see, in this exactly part that is approximate to 0.7, we can see that how we can understand that is happening. It's like the board, when move on, the mass not stays in the same position. Something strange, but that's what happened. And when it goes like 0.9 or 1, it will move rapidly outward, but not for 0.4 or 0.2, that obviously it's gonna go inward, because the angular velocity, the centrifugal force is not too much to be in counter reaction of the gravity. So that's all. If you like the video, please give me a like and a subscription. Thank you.